Good afternoon, Physics 20. I hope you guys are all doing well this afternoon. So, you guys ready for the very last lesson of this unit, inclined planes? So, ladies and gentlemen, as you can see, the pun is excellent. Snakes on a plane. Yeah, very silly movie with I think Samuel L. Jackson's in it, but pun had to happen. All right, so ladies and gentlemen, our inclined plane lesson today is essentially about ramps and how ramps work, and the difference in how the forces are going to be acting on said ramp. Okay, so once you have done enjoying the wonderful puns, we're going to get started. Okay, so ladies and gentlemen, an inclined plane or an inclined surface is when you have your surface is going to be at an angle, so a hill or a ramp, something along those lines. Now, inclined planes are different from inclined forces because an inclined force, the force itself is at an angle, but the object is still moving linearly. So that means the surface is going to be flat. And what is going to be changing is going to be your normal force, or the force of friction, if you're going to be pulling upwards or downwards on that object as you're moving it. However, as an inclined plane, we are going to be having our forces, not just our forces at an angle, our object is also going to be moving at an angle as well, so either up or down a ramp. Okay, now, instead of using either horizontal or vertical when we're going to be looking at our forces, we are going to be considering our forces to be parallel to the surface or perpendicular to the surface. So that in of itself is going to be different. So keep in mind our normal force is always perpendicular to the surface and Fg is always straight down. So that is going to cause a few challenges for us when we're going to be building our free body diagram. So how we're going to do this is we're going to start by looking at how to build a free body diagram on an inclined plane. And then we've got two practice problems that we're going to work through. And that will be your unit. Okie dokie. So I'm going to scroll down here. And we are going to draw a really, really nice inclined plane here. I'm going to zoom in even a bit here. So then that way we've got more space to write on. There we go. Okay. So we're also going to be labeling our forces here, and all of your inclined plane questions are going to work in the same manner. So I'm going to use red to draw some of our basic shapes here. So here is our lovely ramp. I'm going to make this a nice large ramp. We've got plenty of space here. Okay, so here's your ramp, 90-degree angle. And we are going to have a box or object that is going to be on this ramp. Now, we're going to draw a couple of these. We're going to look at if an object is going to be pulled up a ramp or if an object is going to be let to slide down a ramp. In this case, we are going to be having our motion going to be up the ramp. So if you're going to be pulling an object up the ramp, you are going to be having an applied force to drag that up there. Okay? And if you are going to be dragging an object across a surface, you are going to have a force of friction. Now, this is where the difficulty is going to come in, okay? As we are going to need to look at our gravity here. First, let's look at these guys. This guy, notice our friction is parallel to the surface, and force applied is also parallel to the surface. They are not on the x. They have x and y components. So instead of breaking everything into x and y components, which would be painful, we are just going to look at perpendicular and parallel to the surface, which is so much easier. Okay, so I'm going to switch colors. And we are going to go over to blue to look at our next set of values here. Now remember that normal force is always perpendicular to the surface. So that means normal force is going to be going this way. It's perpendicular to the surface. It is not straight up and down, ladies and gentlemen. So be careful of that. I'm going to switch blue to a different shade of blue. And now we're going to look at FG. So as we mentioned earlier, FG is always straight down. Okay, so this brings us to a few challenges here. We can't do a ton of math with this. FG itself is neither perpendicular nor parallel to the surface. But what we can do is we can break FG into its components. We can break FG, being a vector, into different parts. We can have a force of gravity perpendicular and a force of gravity parallel. So what you can do I'm going to break gravity into two different vector components. This, ladies and gentlemen, is FG perpendicular. Now remember that this two perpendicular lines here just means perpendicular. Okay? And two lines like this is going to mean parallel. So we can also then break this into a component of FG parallel. This is going to form a right angle triangle. Okay, now do we have something to work with? We absolutely do. We have forces on the parallel, so FG parallel is going to be pulling this object down the ramp, whereas our force applied parallel to the surface will be pulling up. Now notice FG perpendicular and normal force are acting in opposition to each other. So our F net on the perpendicular, ladies and gentlemen, is equal to 0 newtons because we're neither accelerating off the ramp or through the ramp. So therefore, if we're going to make an F net perpendicular equation, we are going to be having our normal force minus our FG perpendicular. So therefore, once we rearrange our equation, your normal force is going to equal your FG perpendicular. Okay? All right. So, ladies and gentlemen, we have another issue to consider. I'm going to go green for this one. Theta. You are going to be given in your assignment questions theta of the ramp. You are not going to be given any other theta. So we have a bit of a problem. How do we use this theta to help us? Because you'll be given the mass of the object, so you can calculate FG, but how can we break this into F and Y components without a theta? We do have a theta. This theta is equal to this theta. Okay, so these two green thetas are going to be the value here. So if this is 30 degrees, that is going to be 30 degrees. Now, in this video, I am not going to get into why that is the case. If you would like to know why that is the case and more detail on the specific breakdown of how we get these three vectors in more detail, I have attached another video from Khan Academy, which goes into a lot greater detail about really breaking down exactly where these vectors are coming from. I'm going to show you how to do the thing, and the video I'm attaching is going to show why we're doing the thing. Okay, so why things happen, why vectors are broken down this way, why green theta here is equal to green theta here. Watch that video and it'll give you all the whys. If that isn't of interest, you don't have to watch that video and you can just do the things that I'm showing you in this one. Sounds good? Okay. So when I'm going to make an F net parallel equation, I am going to need to consider several different components here. I am going to have to consider my force applied. Now, my force applied is going up the ramp, so that's something I'm going to want to keep in mind. And now my FG parallel always goes down the ramp. So that means FG parallel in this case is going to be negative because it's opposite to our direction of motion. And then we are also going to have our force of friction. So our force of friction is also going to be negative. All right, so those are going to be the forces you want to keep in mind on the parallel, and whether they're going to be negative or positive is going to depend on your motion that we're going to be going on. We've already looked at F net perpendicular over here. So ladies and gentlemen, that is how you're going to be considering something if it's moving up a ramp. We're now going to redraw this a little bit to look at how things are going to move if we go down a ramp. Okay, so I am just simply going to bring up my eraser here, and I'm going to erase this now. We're going to use some of the same diagram. We're just going to change a few different components. Now, our F net on the perpendicular is going to be the same. Your normal force is still going to equal your FG perpendicular. That part doesn't change. What I am going to change is going to be the direction of my motion. So my motion is now going to be going down the ramp. Okay, so this force that is going to be going backwards is no longer going to be my force applied. The force going backwards is now going to be my friction. If you are going to be pulling an object down a ramp, then that means that our F net on the parallel, in this case, when our motion is going downhill, is going to equal our force applied. Now, this is the difference here, ladies and gentlemen. Notice our FG parallel now. Our FG parallel is always going down the hill. So that means our FG parallel here is going to be a positive value as opposed to a negative value. And as always, our force of friction is going to be opposing motion, so it will be a negative in comparison to our force applied. So that's the big difference there. I think my dog is throwing her bone around the living room. She's noisy. Okay. All right. So that's if you're pulling an object down the ramp. Let's look now if we're going to let an object just slide down a ramp. If you're going to be letting an object slide down a ramp or coast down a ramp, that means there is going to be no force applied. And that means you're only going to be having force of friction and FG parallel acting on that object. So in that case, I am not going to have my force applied. I will just have my FG parallel and my force of friction. All right, so that would be what your F net would look like. Now, if you're going to have an object sliding down a frictionless ramp, which in reality doesn't happen, but for sake of argument, if that doesn't happen and we have a frictionless ramp, that means we're going to be having an object sliding down a ramp with not being pulled and without having any friction. So in this case, our F net parallel is going to equal our FG parallel. Okay, so ladies and gentlemen, that is how we draw our lovely force of friction diagrams. Oh, hello, Freya, who's a good girl. Yes, you have a bone. What a good dog. Yeah, she's bringing her bone to show me. Yes, what a good girl. Okay. All right. So, ladies and gentlemen, if you would like to look at the Y's of where all these vectors come from, and if we're going to be looking at the y green theta here equals green theta here, pause the video and go and watch that Khan Academy video that is I've also included with the lesson. You're also welcome to pause the video and and go and watch the field trip where I will be sliding a book down a ramp. I'm fairly certain you can guess what book I'm going to use. Exactly, the Dynamicist. Book named The Dynamicist has to be used in dynamics lessons, guys. Has to happen. All right. So give those a pause and then watch those other videos, and then we will be back. All right, I'm assuming you've paused and watched those other videos now. We're going to scroll down here, and we are going to look at how to do some of these problems. Yes, Freya. She's spoiled. She wants me to hold her bone while she chews on it. I don't know why she likes doing that so much. Okay, so ladies and gentlemen, a boy on a toboggan is sliding down a snow-covered hillside. The boy and the toboggan together have a mass of 50 kilograms, and the slope is at an angle of 30 degrees to the horizontal. Find the boy's acceleration if the force of friction is 64 newtons. Okay, so ladies and gentlemen, as always, our first thing we're going to do is draw a free body diagram. You're going to love free body diagrams by the time we're done with this. They're awesome. Okay, so we are going to have a slope. There's the horizontal, there's the ground. And here is the boy on a toboggan. And he's going to be sliding down the hill. So his motion is going to be that way. Freya, I'm not playing fetch with your bone. I'm not throwing bones across the room. Yeah, there you go. You can chew on it, but I'm not throwing it for you. Okay, so let us think about our forces. We know we have a force of friction. Now, key word. The boy is sliding down a hillside. He's not being pulled down the hill on his toboggan. We have no force applied, so we're not going to add that force there. We have a normal force, which is going to be perpendicular to the surface. We have a theta of 30 degrees on our slope. And we then are going to have our force of gravity. I'm going to make this triangle on our force of gravity here larger than necessary, just so it's easier to see. So this is not going to be to scale, ladies and gentlemen. We have our FG. We have our FG component, which is going to be on the perpendicular. And we have our FG on the parallel. Okay, so ladies and gentlemen, we know this is going to be a right angle triangle, and we know this angle here is going to equal this angle here. If you're curious as to why that is the case, then watch that Khan Academy video, which explains it just beautifully. I'm not going to mess with perfection on that one. Okay, so ladies and gentlemen, let's think about what we need to know. We want to find the boy's acceleration. So let's think where he's accelerating. Is he accelerating on the parallel to the surface or the perpendicular? Exactly, the parallel. So we're going to need to build an F net equation for the parallel to figure out his acceleration. So our F net on the parallel is where we have acceleration. And let's go and look at our forces. FG parallel, the portion of gravity acting on the parallel, is going to be pulling him down the hill. So we have that force. We have no force applied because he's just sliding down the hill. And then we have the force of friction. That is going to be opposing his motion. Well, we already have the force of friction that has been given to us as 64 newtons. However, our FG parallel we don't have, so we're going to have to figure that out. And we know that our F net is going to equal MA. So that would be MA on the parallel would equal our FG parallel minus our force of friction. So here, take your bone. You take your bone. So now we're going to need to find our FG parallel. So let's look at this here. Well, we have a triangle with 30 degrees here. We have a way to find this. We have the boy's mass. The FG of the boy is going to equal mg. So Fg is going to equal his mass of 50 kilograms times our 9.81 meters per second squared. So Fg, so the boy's weight, is going to equal the, oh, hi Freya, yes, is going to equal the lovely value of 490.5 newtons. Okay, now when we come back and look at the triangle, FG is our hypotenuse. Here is our theta. My FG parallel is opposite to my theta. So my FG parallel, I'm going to use sine in order to get. Okay, so my sine of 30 degrees is going to equal my FG parallel divided by my regular old FG. So when I rearrange this, I'm going to multiply FG on both sides. So FG sine of 30 is going to give FG parallel. Okay, so I'm going to put this into my calculator. Oh, excuse me, Freya. Yes, life is hard. Yes, as you can tell, it's a hard life for the dog. Yeah? What are you complaining about? What are you complaining about? Oh, this one. Okay, excuse me. Sorry, she wanted to chew on the other bone while I held it. She's spoiled. She's so spoiled. Okay. So once we go, our sine of 30 multiplied by our 490.5 newtons is going to give us an FG parallel value of your 245.25 newtons. Okay. So now that we have our FG parallel, we can now go plug that into here, and we are then going to be able to calculate our acceleration. Okay, so we're going to scroll downwards here. Okay. All right, so we have our mass, which is 50 kilograms. So we're going to divide by our mass on both sides, and that's going to cancel. Our acceleration on the parallel is going to equal Fg parallel minus our force of friction divided by our mass. Okay, so Fg parallel, we calculated that value over here. So that many newtons. And your force of friction, which is given to you, is 64 newtons. We are going to divide this by our mass of 50 kilograms. And we're going to wind up, once you put that into your calculator, as we're going to get 3.625 ... meters per second squared. Now, ladies and gentlemen, I didn't set a magnitude of acceleration. I absolutely set acceleration. So I want direction with those vectors. And we want sig digs, which is 2, so 3.6 meters per second squared. And for this one, please don't write down. Please write down hill or down the hill or down the slope or something along those lines, because down is down, downhill is downhill. So if you just say down on your answer when you calculate acceleration on your assignments, I nearly said test. We don't have tests. Sorry, guys. All right, so if you write just down, you're losing half a point because your vector, your direction on your vector is wrong. Downhill is correct. Okay, so ladies and gentlemen, there's that one. Let's now make it more complicated. Yeah, now we're going to find mu. Woohoo! All right. Scrolling down. Okay, this one's fun. So, ladies and gentlemen, we have an applied force of 46 newtons is used to push a 45 kilogram block up an inclined plane with a slope of 35 degrees to the horizontal. If the block is accelerating at 2.6 meters per second squared, what is the coefficient of friction between the surface and the block? Okay, we got a lot of stuff going on here. So as always, free body diagram. So then that way we can see what exactly is happening here. So I'm going to take up a bit more space to draw our free body diagram because there's more stuff to put onto it. Okay, so here's our surface. The parallel, I guess. And here is our ramp. That's 90 degrees. And this is our 35 degrees. Here's our block with a mass of 4.5 kilograms. And we're pushing the block up a slope. So that means our force applied is going to be up. So our motion is going that way. Okay. We have a force of friction here. So that means we can absolutely calculate mu. We have our normal force. Remember that, ladies and gentlemen, that normal force is not straight up and down. It's perpendicular to the surface. Okay. Fg, however, ladies and gentlemen, Fg is straight down. We are going to break this into our Fg perpendicular and into our Fg parallel. Okay, this is the 90-degree angle. This is 35 degrees. So let's just get our value of Fg right off the bat. Let's just do this right here. So our mass is our 45 kilograms. We're going to multiply that times 9.81 meters per second squared. And I'm going to scroll down a wee bit so I got space to write. Okay, so our Fg is going to be equaling our 44.145 newtons. Okay, so we have our regular old Fg. We have our acceleration of 2.6 meters per second squared going up that hill. We have been asked to calculate mu. Okay, so in order to do this, ladies and gentlemen, in order to calculate mu, when we look at our equation, force of friction is equal to mu Fn. Well, in order to get mu, we need the force of friction. And in order to get mu, we need the normal force. So we are going to have to do two different things in order to calculate this. We're going to have to calculate normal force, and we're going to have to calculate our force of friction. So let's do the easy one first. Let's calculate our normal force. So remembering that our normal force is perpendicular to the surface. So our F net on the perpendicular is going to equal my Fn minus my Fg perpendicular. So remembering that from earlier on in the video. So that means because we're not accelerating up off the ramp and down through the ground, our F net is 0. So our normal force is going to equal my Fg perpendicular. Well, my Fg perpendicular is here. My Fg perpendicular is going to be this line here. That is adjacent to that 35 degrees, which means I'm going to use cosine. Correct. So my Fg perpendicular is going to be got from cosine of Fg. Okay, so my cosine of theta is opposite over adjacent, so is Fg perpendicular over straight old Fg. So when I rearrange this, my Fg times cosine of 35 is going to be my Fg perpendicular. All right, I'm going to scroll down so I don't write on my face. So my FG is 44.145 times cosine of 35, making sure your calculators are in degrees. No rad time in physics. Rad time. And that's going to give you your FG perpendicular, which once you plonk that into your calculator, you're going to wind up with a value of 36.161 dot, 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 dot. Well, ladies and gentlemen, remembering that this is equal to our normal force, we can just equate that. Okay, so ladies and gentlemen, with our mu Fn, we now have our Fn. So that part is good. Now, the next piece we're going to need to get is our force of friction. So let's come back to our free body diagram here, and we're going to look at this force of friction here. That force of friction is on the parallel. Well, sorry, someone had the audacity to walk past the house. The dog needs to warn everybody. Yes, protecting us from all things evil. Okay, so we now need to make an F net equation on the parallel. We know we have a F net because we're accelerating up along the parallel. We know we have a force applied, and we also have the ability to get our FG parallel. So we have and then we can use those to find our force of friction. Okay, so ladies and gentlemen, I'm going to scroll down here so that way we have some space in order to write. I'm just going to leave these values visible here. Okay, so let's start by making my F net equation. So my F net on the parallel is going to equal my force applied, which is going up the ramp. Okay, so you want that number to be positive. That's a direction of motion. And now FG parallel is going to be opposing motion. So not only when you're pushing an object up a ramp do you have to oppose your friction, you also have to oppose force of gravity on the parallel. Okay, so then we also have minus our force of friction. Okay, well, I'm going to just rearrange this because I can. And we want to have our lovely force of friction to be on the other side. Okay, so ladies and gentlemen, once we rearrange this lovely setup, we're going to wind up with our force of friction is going to equal my force applied minus my force net minus my FG parallel. Okay, so ladies and gentlemen, let's start thinking about the components that we're going to need here. Well, my F net is MA. So I am going to just put that in there because I can. Oops, let's fix that. Okay. All right. Well, ladies and gentlemen, we're trying to find force of friction. We've been given the force applied. We have the mass, we have the acceleration, but we do not have our FG parallel. So that is what we're going to need to calculate now. Okay, so we're going to scroll back up here and we are going to look at our FG parallel. FG parallel here is opposite to that 35. So that means we're going to be using the sine in order to solve for this. So we are going to be using sine of 35 in order to get that FG parallel, as well as the FG that we calculated earlier. Okay, so for our FG parallel, we are going to have our FG parallel, which is our opposite, and our plain old FG, which is adjacent, is going to equal my sine of that 35 degrees. So we're just going to multiply that FG out on both sides. And we're going to wind up with FG parallel is going to equal sine 35 times our FG. So once we solve for this, your FG parallel, sine 35 times our 44.145 is then going to equal our... Lost my spot, ladies and gentlemen. Lost my spot. There we go. 25.3205 newtons. Okay, so now we've got all the bits we need in order to find our force of friction, which will then allow us to find mu. So our force of friction is going to equal, we have our force applied, which is our, given to us, 46 newtons. We're going to subtract this from our 50 kilograms times our acceleration of 2.6 meters per second squared. And we will then subtract that from our 25.325 newtons. Whoops, that's not FG. I want FF. There we go. So our force of friction, ladies and gentlemen, is going to be the lovely value of our 8.9746 ... newtons. Okay. We're not done yet. Almost there. Almost there. Okay, we now need to find mu. So remember, ladies and gentlemen, how force of friction is mu Fn. So we're going to divide our force of friction divided by our normal force, and that is going to give us mu. So I'm going to scroll down so I can put numbers into this. So force of friction, we just calculated, so 8.9746, all digits in your calculator. And then we're going to go all the way back up to where we originally calculated our normal force there, which is that 36. So we're going to grab our pen again, and we are going to go 36.16 ... all the digits from your calculator when you calculated Fn. And throw your values in there, and you're going to get your 0.24315 ... Okay, I'm going to make a mistake, and I want you to tell me where I would be deducting myself half a point. So my mu is 2 sig digs. So I dropped a number, I dropped an 8. There we go. So 0.25, and as always, I need to give units. Where did I screw up? Where would I be deducting myself half a point? Exactly, the units. Mu is unitless. So if you give me units for a unitless number, I deduct half a point. Okay, so the reason why mu is unitless, well, let's put our units back in here with our force to do some unit analysis here. Well, units for force is newtons, newtons over newtons. Well, newtons divided by newtons cancels out. So that means we have no units. They have canceled out. So therefore, we have no units. Okay, so ladies and gentlemen, I hope you guys found that interesting. We've got some practice problems here for you guys to have a try at. And then we've also got some practice problems here for you as well. Have a look at that Khan Academy video if you want to see the whys as to those forces and where they come from. And also have a look at the field trip video. That's the word I'm looking for. So we can watch the dynamicist slide down a ramp. All right, guys, have a good day. No fires, injuries, or explosions. Now I can't turn this thing off. There we go. Have a good day, guys.